Hello students, myself Suraj Gupta, an assistant professor in mechanical engineering department at MLV Textile Engineering College, Bhilwara. Today we are going to start a topic response of rotating and reciprocating unbalanced system. This is the part 2 of the previous lecture in mechanical vibration. So moving further, we have the topic rotating unbalanced system. So a machine having a rotor as one of its component is called a rotating machine, like turbine and IC engines. So if we are consider this is the rotating system, which in which unbalanced mass of m0 is situated from the center of mass of the total system at a distance of e. So it will experience a centrifugal force of m0 e omega square, that if we are considered this is equals to f0. It will have an instant, it will have a angular position of theta, that is equals to omega into t. So it will have a vertical component, that is m0 e omega square sine omega t, and horizontal component will be m0 e omega square cos omega t. So the total mass is m0 plus mass of the rest of the body, that is m0 is the mass of the rotating unbalance. So now we are going to do the free body diagram. So the total force in upward direction is the m0 e omega square sine omega t, and horizontal is the m0 e omega square cos omega t. This will be cancelled out because this mass is not moving in this direction, so this will be cancelled out because of some support from this side. So the total motion is going in the x direction. If this motion is uh, displacement is occurring in this x direction, so the total force in the vertical direction is the m0 e omega square sin omega t. In that case, the spring force will be kx, and the damping force will be cx dot, and dl number is the mx double dot. So total force will be this force. Total downward force will be this total force. So this is the total downward force, and this is the total upward force. So we are going to take this term as a f0. This is m0 e omega square, this is f0. And we have done this type of free body diagram for the previous lectures, in which we have the formula a equals to f0 by k, a root of this term. This term is you have to remember every time in the vibration. So this is like f0 by k, but we are going to multiply this m upward in numerator by m at numerator and denominator. So this will be simplified in this form. So this is m0 by m multiplied by e, this is omega by n, omega n, and this omega by omega n is frequency ratio. So this is r square, this is e, and this is mass ratio, m0 by m. m0 is the mass of unbalanced system, and m is the total mass of the system. So we are going to take this term in the denominator of a. This term is will be this expression. This is r square divided by root of 1 minus r square to the power 2 plus 2 zeta r whole to the power 2. That we have already find. This is z by b. What is this? This is the motion transmissibility, and here it is the unbalanced force transmissibility. So the motion transmissibility is always equals to the force transmissibility, but here the motion is the relative motion, because this is z. We have done this previously in the class. So remember this formula, this is the same. So at resonance, r equals to 1. So r equals to 1, putting this value r equals to 1 in this equation, this will be 0, and this will be root of 2 zeta whole square, and this is 1. So 1 upon 2 zeta, because root of 2 zeta whole square, so it is 2 zeta. So remember this equation also. Now we are going to draw the characteristic curve for this ratio. So this is a term, and this is another term, a by this term. So this is we have done this will be same as for the uh, this is as for b by z by b, sorry, this is z by b. This we have done previously. This is z by b, this is z by b, this is equals to z by b, as same we have done previously, z by for z by b. So this curve is can be clearly understand in the uh, excel. We are going to see the excel form of this equation. So if you remember this equation, if you see this equation, in this equation the r square divided by 1 minus r square to the power is 2 plus 2 zeta r to the power 2. So in this, if we put r value from 0 to 10 and the at a certain interval 0 0.1, 0 0.2, 0 0.3, we will have different value of transmissibility, means ratio, the ratio of a by m, 0 by m multiplied by e. So at a different value of zeta. So now in this curve is for zeta equals to 0. At zeta equals to 0 we can have the value of zeta equals to 0 and putting the value of r equals to 1. In that case we will have the value of transmissibility will be infinite. But here in this case, but here in this case but at r equals to 1 and zeta equals to 0, the value of transmissibility will be something will divided by 0, that is equals to infinite, but the excel is not able to show the value at infinite. So this curve is after this point is different, and before this point is different. So because it is tends to infinite, and here it is also tends to infinite, it is going to the infinite and it is coming from the infinite, and curve is like this. But at infinite it is not able to show the value at infinite. So we are going to change the value of zeta 0.2. Then we can see the value has been changed like this, and the maximum value is 2.5, and it is going to be unity. So now we are going to change once again 0.4. Then we can see the maximum value is decreased, maximum value is below 1.4. So we can see the maximum value of the every curve is decreasing if the zeta is increasing. You can see this maximum value is below 1.2. Now 0.8 is different, at 1 it is different. If we are increasing 6 up to 6, this is different, this is going to be straight, but it is tending towards unity, it is tending toward unity. So we can see that every curve will be unity if the value of r at a certain after certain value of r, the value of transmissibility will be unity. So the combined transmissibility curve are like this. If zeta is decreases, increases in this way, increases in this way, the value is, the maximum value is decreases, and all the values will be unity after some value of r. This r value is almost equals to 3. After that all the value of transmissibility at a different zeta will be in unity means 1. So the curve is like this, the same. After this r equals to 3, the value, all the values are tending towards unity. So the some important points will come out from this characteristic curve, that is the if the damping factor, the damping factor will plays a very important role for during resonance. Means at the if the damping factor is decreases, we can this value will increases. So we do not want this to be increases. So if zeta is decreases, then this will be increases, but if we increase the zeta, we will have the value of this ratio will be decreased. So we should put the value of zeta maximum as much as we can be. If omega is very less, r is tends to 0. Omega is very less means r is tends to 0, means r equals to omega by m, omega n. If omega is very less, so r is tends to 0. If the r tends to 0, we can see this value is tends to 0, means this ratio will be 0. If omega is very high, we can see this omega is very high, so r is very high. So at high r, the value, all the value of transmissibility at different zeta will be 1. So at very high speed it is 1, means it is a constant value, so no effect of zeta, because every zeta value curve is met at 1 and tending towards only 1. It is not going to be changed, it is constant. And at resonance r equals to 1, and r equals to 1, and that case the formula will be, the amplitude formula will be this, and you have to learn this formula, because the direct numerical will be asked from this formula. Now the reciprocating unbalance. Considering a reciprocating engine as shown in the figure, this is the reciprocating mass which is unbalanced m0. We have done in the theory of machine subject that piston is moving up and down, reciprocating motion taking place, and the system having a mass of m, and it is consist of a spring k by 2 and k by 2. This k by 2 is showing that these are in the parallel, so the combined effect of this spring will be the stiffness of k, and damper is c. So length of the crank is e, the length of the connecting rod is l, and we are assuming that this crank length is very less than the connecting rod length. So inertia force due to the reciprocating mass is approximately to the m0 e omega square sine omega t plus e by l sine 2 omega t. And we have assumed that this e is very less than l, so e by l is tends to 0. This we have done in the subject theory of machine. So this term is known as the acceleration of the reciprocating body, means here reciprocating body is piston. So total force is mass into acceleration. So this is the inertia force. So this inertia force will be the same as per the D'Alembert principle. We have seen this. This is the inertia force. To balance the inertia force in the rightward direction in this equation, we have this formula. So the same formula will be applied for the reciprocating unbalanced system. So the formula will be same for the transmissibility. So we can have the same important points for the same numerical, and we will the conclusion is same and characteristic curve is same for the reciprocating unbalance. So we have completed this third unit. Up to this, we will solve some numerical problem, and you should upload the all the solution of the numerical problem that we have. I will share all the numerical problem on the Google Classroom, and you have to solve all the numerical problem and upload it on the Google Classroom, so that I can check all the activities of the students to for your better assessment. Thank you.